Welcome everyone who has joined so far and who is going to come in during the talk. This is a kind of introduction to A.N. Mitra Memorial Function, which will be today and tomorrow, April 14th and 15th. And I am, of course, a retired person from the University of Delhi, Panchapakesan. First of all, I would like to wish you happy Baisakhi, because today is the Baisakhi day for the whole of India. Happy Tamil New Year. Tamil New Year is being celebrated in South India. Then remembering Baba Saheb Ambedkar on his birthday. Baba Saheb Ambedkar was an extremely great leader of India who had a big hand in making the Constitution of India. And finally, of course, A.N. Mitra's birthday. It's actually tomorrow, and the function will be today and tomorrow.
Should we go to the next slide?
One moment. Yeah, I'm going to begin with talking about the obituaries of 4 people who died within the last 1 year. And I know 3 of them very well. The 4th one, I've heard of him like every one of you else have. The first one is Vaideshwaran Rajaraman. He's a great legend in computer science. The second one is Ramamurthy Rajaraman, who was a beginner of the many-body problem in nuclear matter, which was the pursuit of Professor Mitra for his whole life almost. The third person was Ayalam Parameswaram Balachandran, or AP Balachandran, who was in Syracuse University and who had a very strong and powerful group on mathematical physics during his lifetime. The fourth one is Anthony Leggett. You all might have heard of him. He's a Nobel laureate who worked on helium-3 and later on worked on the combined effects of both classical and quantum mechanics, and how do you go from one to other. Vaideshwaran Rajaraman, or V. Rajaraman, is the first person I want to talk about. He was my classmate in Madrasi Education Association School in Delhi and St. Stephen's College in Delhi. And later on, before becoming a legend of computer science, he joined IIT Kanpur in 1961. And he moved to IISc Bangalore about 10 or 15 years later. And he wrote 23 inexpensive best-selling textbooks, many of them with his wife Dharma. And they became almost the mainstay for many of the students and teachers of computer science. He became an extremely well-known name in India and abroad also for teaching and research in computer science. Of course, as I told you, he was my classmate. I know him very well, and we lost him in November 2025. This is his photograph, V. Rajaraman. And as I told you earlier, he was with me in both MEA school and St. Stephen's College. The next person I want to talk about is Ramamurthy Rajaraman, who was 6 years younger than me, but was also in Madrasi School, or MTEA High School as we called it, and St. Stephen's College, Delhi. And he died on 12th of June, 2025. And he looks like this. And many of you must be knowing him personally because he taught in Delhi for quite a few years, besides studying in Delhi and doing mathematics. As you can see, or as I told you a little bit earlier, he started working on his PhD in Cornell University with Hans Bethe in 1963. And he made lasting contributions to 3-body and higher number of body interaction in his thesis. He showed that the Bruckner-Goldstone theory does not really converge, but it is a series in the density or equivalently in the number of particles in the nucleus. And after he published his thesis, a year or two later, Bethe himself took up the problem and more or less completely explained the problem in 1965. And in 1967, Bethe and he wrote the review of this problem. And it is really surprising that A.N. Mitra started studying the problem, in fact, a little bit earlier. He started studying the 3-body interaction in 1961. And he had the greatest regard for, of course, Professor Bethe and Professor Rajaraman. Many times he has told me Rajaraman has done tremendously great work. And of course, before Rajaraman went to Cornell, he went and met Mitra, found out how Cornell was, and then moved to Cornell. The third person I want to talk about is Ayyalam Parameswaran Balachandran, AP Balachandran. He did his PhD with Alladi Ramakrishnan in Math Science, Chennai. And later on, he was a postdoc at the University of Chicago. And then he moved to Syracuse University, where he had a well-known mathematical physics group, headed by him and Kamesh Wali. And I visited that group in 1982. And at that time, they had just finished studying skyrmions. And Witten had also come just before I reached there. And he talked to them for a long time and went back and wrote another paper on skyrmion, which also became very famous. And later on in the 1990s, Shivaji Sondhi, who many of you or some of you at least will have heard of, applied the idea of skyrmions to quantum Hall effect. And in doing that, he made use of R. Rajaraman's book on solitons, which was also very helpful. It's a small world in some senses. Yeah, finally we come to Anthony Leggett, who was born in 1938 and died last month on the 8th of March in the year 2026. His Nobel Prize work, for which he got the Nobel Prize in 2003, was on quantum phase transitions in helium-3. Helium-3 itself is a fermion, and it cannot undergo Bose-Einstein transition. But like in superconductivity, when two helium-3s combine, they become a boson, and they can form a Bose-Einstein condensation. He studied this and derived many remarkable results. But he also moved on to study how big can a quantum system be. And he also predicted system. In fact, he said there should be a Josephson junction system, which is fairly big and which can show quantum effects. And amazingly, this Josephson junction was created by few experimental people 45 years ago. But unfortunately or fortunately, they got the Nobel Prize for it only now. Because now they've realized the relation between quantum and classical physics probably is entering a very crucial stage. So relation between classical and quantum mechanics is still not understood fully. And that is what I'm going to speak about in the last few minutes. This is Anthony Leggett, for those who may not have seen him. And this is his description. And then we come to quantum mechanics to classical mechanics. Initially, in the 1930s, when quantum mechanics was discovered, von Neumann talked about the fact that when you make a measurement, there has to be a collapse which takes you from quantum mechanics to classical mechanics. But this collapse, as he called it, does not obey unitarity, does not obey time reversal invariance in the transition. But you may ask a question, if in the collapse, there is a detector. And if that detector is also included in the system, you get another bigger quantum mechanical system, which again can be studied. So can you go on enlarging the system like this from smaller to bigger to bigger to bigger? Wigner in 1960 thought this will probably end in the human consciousness. It can be consciousness of Wigner, or it could be any other human being. And Wigner called him my friend or somebody like that. So he's known as Wigner, or Wigner's friend consciousness is where quantum mechanics become classical mechanics. In Zurich in 1990s suggested decoherence by environment. That is the cosmic microwave background radiation that is there, which cosmology tells us is there and which has been experimentally observed. This is what brings you down to classical mechanics from quantum mechanics. And so Wigner liked this idea. In 1990s, he said, I withdraw my other suggestion and we should follow this suggestion. But more recently, in the last 10 or 15 years, it is being increasingly felt gravitation must be also playing a big role in this. Roger Penrose thinks so, and he has his own ideas of how it works. And then black holes may also play a role. And Stephen Hawking, using quantum methods in curved space-time discovered emission of thermal radiation by black holes. Black hole has a temperature and it emits a thermal radiation. This leads to information loss or violation of unitarity. So there is still no agreement on what happens or why. No wonder Feynman, talking about quantum mechanics, says in his lectures on quantum mechanics, anyone who says he or she understands quantum mechanics does not understand it at all. So the talks in this meeting today, I think, are also going to either talk about or skirt around the boundaries of this particular topic. Let me just remind you that measurement and collapse of wave function takes one to decoherence in classical mechanics is called the Copenhagen interpretation of quantum mechanics, and it was given by Niels Bohr. And the interpretation of quantum mechanics is one of the key main problems which is still unsolved, and going beyond Copenhagen interpretations seems absolutely necessary. Thank you so much. I hope you enjoy all the talks, and or at least as many of them as possible, and hope we will all benefit by listening to all these talks. Thank you so much.
Thank you so much, Professor Panchapakesan. Thanks. Thank you so much.
Dear and esteemed colleagues, I have been requested by the organizers to say a few words about the physics of Professor Vidyasagar Bhasin. It's my proud privilege and honor to do so. Professor Ashoknath Mitra, arguably a doyen of theoretical physics in modern India, had secured an iconic status amongst his students and colleagues in his lifetime. Notwithstanding his stellar contributions to theoretical and nuclear particle physics, Mitra's true legacy will remain the generations of students whom he taught and inspired to embrace physics. Professor Vidyasagar Bhasin happens to be one of the more illustrious of Mitra's students. The next 10 minutes or so are meant to recall his contributions to theoretical nuclear and hadron physics. Vidyasagar Bhasin received his PhD in theoretical nuclear physics from University of Delhi, working on the problem of nuclear three-body scattering at low energies. He has spent extended periods at ICTP, Trieste, SLAC, Stanford University, T.W. Bonner, Nuclear Lab, Rice University, University of Manitoba and Winnipeg, at different times as postdoctoral fellow and visiting scientist. He has been Alexander von Humboldt Fellow at the University of Bonn. He taught and carried out research at the Department of Physics and Astrophysics, University of Delhi, for more than 4 decades. His research interests have been in non-relativistic and relativistic three-body nuclear physics, high-energy scattering problems, meson-baryon physics in quark model, charge symmetry breaking effect in nucleon-nucleon scattering, few-body analysis of structural properties of neutron-rich halo nuclei, and search for Efimov effect in the atomic nuclei. He has edited several volumes on some of these topics and has authored several books on science and technology for the National Center for Education, Research and Training, NCERT, Government of India. Now, I would like to mention some of the significant contributions of V.S. Bhasin. Due to paucity of time, I would necessarily be brief and rather selective. Faddeev, starting from the Lippmann-Schwinger equation for the three-body scattering problem, showed how the problem of disconnectedness of the scattering matrix appearing in the form of delta-type singularities inherently present in the Lippmann-Schwinger equation can be resolved, leading to the three-body kernel, which is completely continuous. Subsequently, Lovelace in 1965, following Faddeev equations, undertook a detailed study and found that in situations where the two-body systems involved have bound or resonant states, the two-body T matrices could be represented in a separable form, with the result that resulting integral equations for the three-body scattering amplitude would involve only a single variable. Such equations could be easily handled computationally without resort to further approximations. Prior to this, Mitra in 1960 had already initiated a three-body approach using two-body separable potentials. And in 1963, Bhasin, as part of his thesis work under Mitra, derived using three-body Schrödinger equation the same equations as obtained by Lovelace for the ND scattering problem. The three-body formalism using separable potential in the S and P states of nucleon pairs was set up under the conditions of full antisymmetrization of the three nucleon wave function. The formalism was applied to the problem of neutron-deuteron ND scattering, where the effects of polarization were fully taken into account. The amplitudes for quartet and doublet scattering were found to satisfy 2 and 4 coupled one-dimensional integral equations, respectively. Now, independently, Sitenko and Kharchenko also obtained similar equations using Faddeev's theory and employing separable two-body matrices. Bhasin, along with Schrenk and Mitra, a few years later, provided a more accurate evaluation of low-energy ND scattering length and ND phase shifts. During the same period, Amado and his group, starting from the Lee model, developed a three-body model for ND scattering, which eventually led to similar equations obtained with separable potentials. Thus, these attempts carried out all together during 1960 to 65 sparked off a spectacular interest in research activities in few-body nuclear atomic and molecular systems at various places all over the world. The major impact of this was the decision to hold regular international conferences after a period of every 2 years in different parts of the world to sustain the interest and encourage the young researchers in this field of few-body physics. Just 3 years on the heel of the ND scattering work, Bhasin, along with Mitra, analyzed the possible existence of a bound tri-neutron state in a much cited work in the physical regulators. Thanks to Pauli principle and the absence of Coulomb repulsion, the tri-neutron or N3 problem, N3 provides a rather clean system for theoretical analysis. Bhasin and Mitra basically discussed the role of the POA forces in the NN interaction and concluded that the non-existence of the N4 state need not necessarily imply that of N3. Much later, Bhasin, along with Mitra, calculated TDN and TD*N vortices via spectator functions. Other than his pioneering work in non-relativistic three-body scattering problem, Bhasin produced a large body of work in the 70s and 80s in different topics, like photoproduction of pions, quark model for meson baryon processes, nucleon-nucleon interactions with tensor interactions in quark compound bag model, charge symmetry breaking effect in nucleon-nucleon scattering from the quark model, etc. From middle of 90s, revisiting the techniques of separable potentials in three-body systems, Bhasin has produced an impressive body of major works in the structural properties of two-neutron halo nuclei and the search for Efimov effect in such nuclei. Over a long collaboration with Indranil Mazumdar, he has studied structural properties of a host of two-nucleon halo nuclei, both Borromean and non-Borromean. Within the framework of their three-body analysis, they have produced the structural properties of halo nuclei like lithium-11. They have analyzed and showed how non-Borromean nuclei like 20 carbon are more vulnerable to support Efimov states vis-a-vis Borromean nuclei like lithium-11. Bhasin, along with Mazumdar, also studied the evolution of Efimov states in nuclei like 20 carbon to resonances. In a very significant and much cited work, Bhasin, Rao, and Mazumdar, they have showed the manifestation of the Fano mechanism in the asymmetric structure of the resonances in a neutron 19 carbon scattering in 20 carbon nucleus. This considerable body of work by Bhasin and his collaborators have resulted in a monograph titled Few Body Dynamics, Efimov Effect, and Halo Nuclei. A man of much accomplishment, but rather unassuming, V.S. Bhasin continues his research with his characteristic honesty, integrity, and zeal. He has not shown any signs of slowing down, even well after his superannuation from Delhi University. A much sought after academic by different government agencies for academic activities, he takes up all his assignments with utmost honesty and sincerity. I remember with a great sense of gratitude his lectures and enthusiastic participation in a meeting that I organized way back in 2010 in TIFR along with my senior colleagues like Professor Rajiv Bhalerao to celebrate the 50th year of Faddeev equations and 40th year of Efimov effect. My lifelong collaboration and association with him has simply enriched me, academically and otherwise. I pay my sincere respect to him and wish him many more years of happy and active life. Thank you.
Thank you so much, Professor Mazumdar.
There are I have a few sentences from Professor Bhasin. If you allow me, I may read it out.
Yeah, please, absolutely. Please.
So this is from Professor V.S. Bhasin. Dear organizers of the A.N. Mitra Memorial Lectures and lectures, my sincere thanks to you all for this felicitation. I am deeply moved. My current indisposition prevents me from actively participating in this meeting. It is most gratifying that leading theorists and some of the most prominent practitioners of few-body nuclear physics have agreed to deliver lectures and also chair the sessions. I fondly recall my past associations and interactions with several of them. I am particularly delighted that the organizers have continued their sincere efforts to organize this series of lectures in the hallowed memory of the late Professor N. Mitra, my guru and lifelong collaborator. The selection of the speakers, stalwarts in the world of nuclear and particle physics, is a perfect tribute to the memory of a great Indian theorist who stood tall on the international stage. Thank you very much, and my best wishes to you all. Thank you.
Lovely. Thanks so much, Professor Mazumdar, for that beautiful summary of the contributions of Professor Bhasin. It would have been so very nice if he could have been able to join in online. But in lieu of that, I think we all have been able to get a fairly good idea of the impact and the importance of his contributions in the area of free body physics.